Yeah, in this 10 plus minutes of March meeting style talk, I will tell you about this interfacial engineering of magnetic skyrmions. This is actually belongs to a longer talk about when real space topology meets with momentum space topology. But in this 10 plus minutes a brief talk, I will simply explain this part of the story where we can use electric fields to control, to write and delete the magnetic skyrmions at the interface of heterostructure. And this work is in collaboration with my postdoc, Chao-Kai and my grad student, Shuping Yao here. Yeah. So the idea, what is the idea? So the idea is to synthesize two different materials, one with magnetism, the other with ferroelectricity. So the presence of ferroelectric order automatically breaks the inversion symmetry and can be manipulated by electric fields, apparently. The inversion symmetry is broken by the ferroelectric order, and the inversion symmetry breaking will generate the so-called Diron-Schema-Maria interaction between the local moments, and the DM interaction, the Diron-Schema-Maria interaction would necessarily twist the magnetic structure or favor some kind of non-collinear configuration, and this will generate, and under some certain conditions, generate the magnetic skyrmions. So that therefore we have electric field controls, influence ferroelectricity, and ferroelectricity generate DM interaction that generates the non-collinear magnetism, and this includes the skyrmion lattice and includes the skyrmion texture. So this gives you a way to allow the electric field to control skyrmions, although this is rather indirect, and but it works. Yeah. So to implement this idea, we consider the the heterostructure by chromium germanium tellurium and indium 2 selenium 3. And this interface was actually started earlier by Xiang Zhang's group from Berkeley. So in this material, in this interface, the chromium is the magnetic ion. So the indium 2 selenium 3 provided the ferroelectric order. So here we work out the effective interaction between the chromium local moment. As I said, because of the inversion symmetry breaking at the interface by the ferroelectric order, the DM interaction will be generated, and this is a general exchange matrices, including the diagonal part, which is the Heisenberg-like interaction, and antisymmetrical off diagonal, which is the Diron-Schema-Maria interaction, and off diagonal symmetrical one, which is called the pseudo dipole interaction. So gamma term, yeah. So with different electric fields, for instance, we apply the electric field, apply the period to the z direction normal to the heterostructure, or opposite to z direction. So there will be different values of exchange coupling. This is when electric field is up, and this electric field is down, and this is when the electric field is 0. They have completely different exchange coupling constant, and DM interaction is also quite different, right? So to obtain the to try to figure out the magnetic structure, so we are working on all these things. We are working on magnetic orders. So the spin degree freedom, which is chromium is spin 3.5. It's fairly large, and the mean field semi-classical type of treatment of the magnetism would be sufficient. So we use some kind of Ginzburg-Landau, generic Ginzburg-Landau type of free energy to compute the free energy for the magnetic sector. And this is the free energy, generic free energy. Because of this absence of continuous spin rotational symmetry, there are many, symmetry allow the anisotropic interaction of the spins. So this is highly anisotropic, yeah, even at quadratic level. Yeah, and these parameters can be computed from these exchange components that we obtain from ab initio calculations. So this is the first diagram, and with magnetic field, we find for different Maria vector magnitude, we have this kind of first diagram for different dx, the strengths of the interactions. We found for electric field up, the system is along, the physical system is evolved along this solid line, where there is a rather narrow region of skyrmion generation, magnetic skyrmion generation in this region, very narrow, mostly ferromagnetism, all the spin oriented in the same direction, and a very narrow region of spin spirals where spin from spiral periodicity. But if we switch the direction of magnetic field, there's a very large range of parameter, that magnetic field parameter, that the system from a skyrmion crystal. There is the spin equilibrium from magnetic skyrmions, and there is also there's a large region of spin spirals. Ferromagnetism appears when the field is large enough, where the spin polarized to the field direction. So that this comparison between electric field up and electric field down tells you there is the electric field can actually generate, can write or delete the magnetic skyrmions at the interface. Yeah, so this is this idea. When our paper was put up on arXiv and accepted by physical review research, an experimental paper from Qinghua's group by Yonggang Zhao from Tsinghua, they actually experimentally realized this idea independently on different set of material, which is this PT cobalt TA titanium magnetic multi-layer and ferroelectric layer material heterostructure. They actually realize this exactly the same idea, but realizing a different set of interface. Once this is the magnetic layer, and the other is this ferroelectric layer, and they put together, and they can use the electric field to manipulate, generate, or annihilate the skyrmions, and they successfully demonstrated experimentally. And this is the experimental group, by the way. Yeah. So this is pretty much the idea about electric field control of skyrmions in multiferroic heterostructure. And thanks very much.